Welcome dear students. In this video we are discussing interstitial voids in crystals. In the previous video we have learned that in metallic crystals or in any crystals the particles are closely packed such that they make use of the maximum space, leaving out minimum empty space. Since spheres touch only at a point, there will be definitely some empty space left out in any crystal lattice. Now these empty spaces are called voids. So interstitial voids are the vacant space in the close packing of spheres or particles in crystals. Mainly there are three types of voids. Even though these are empty spaces, they have a lot of implications, significances in crystals. One is that it is in these voids certain small non-metals can enter and form what are called interstitial compounds. You might have learned about interstitial hydrides, interstitial carbides, etc., where such non-metals like hydrogen, carbon, etc. can enter these voids and form some compounds. Another importance of interstitial void is that when we explain the structure of ionic crystals, which comes in later course, when we consider ionic crystals, you can see that cations which are so small that they can enter the voids are arranged in the close packing of anions. So the voids are important in the occupancy of cations. And also in solid state conductivity, you can see there are so many semiconductors where you can see that they conduct electricity even in the solid state, and that is also explained due to the presence of voids where some impurity ions can enter and they can move, ionic diffusion can take place. All these are facilitated due to the presence of voids. And also there are some significant optical properties shown by certain crystals, and that's also explained with the help of such voids. So voids are very important. Coming to the types of voids, starting with tetrahedral void. Regarding each void, what you have to understand is where the voids are present, what is the kind of geometry, and how big is the void, etc. See, this is the diagram which we discussed in the previous class while discussing close packing of spheres. In this very diagram, you can identify these two voids. Look, let's take for example tetrahedral void. To understand tetrahedral voids, you consider, see, in the first layer, that is a blue sphere, I am marking this one, the second sphere, and the third sphere here. I am drawing it here. Okay, so these three spheres in the first layer. Now you can see the green sphere coming above it in the depression that I am drawing. So there is a sphere or particle kept in this depression, right? So now how many spheres are in touch here? Total 4. There are three spheres in one layer and one sphere in the next layer. 4 spheres are touching each other. This is the situation. You can see 3 spheres in one layer and one above it in the second layer. This kind of arrangement is so many there in this arrangement. There are so many such arrangements here. Now you can see there is an empty space at the center. This empty space inside is called tetrahedral void. So what is tetrahedral void? You can note the point. Tetrahedral void is the empty space at the center of 4 touching spheres. And why it is called a tetrahedral? It is because if you join the center of these four spheres, that means this is the center of these three, and this sphere is actually out of plane, right? Because this is above this layer, so it will be here. We cannot show the point here, so we can show it somewhere else, shifted. So if you connect these three and one point out here, I can draw it like this. The point, the center of the sphere above this, suppose it is shown out here somewhere, and connect to all these corners. You can see that this looks like a tetrahedron, right? And the empty space is somewhere at the center of this tetrahedron, somewhere here. This empty space will come, and this is called tetrahedral void. So this is called tetrahedral void because if we join these four spheres, gives a tetrahedron. So I repeat, tetrahedral void is the empty space at the center of four touching spheres whose centers lie at the corners of a regular tetrahedron. Okay? The empty space at the center of four touching spheres whose centers lie at the corners of a regular tetrahedron. Right? It's very clear. If I join the center of these three spheres, you get a triangle, and there is one sphere above it, and if I join the center of this sphere to all these corners, you get a tetrahedron. And this empty space is at the center of this tetrahedron. It's clear. You can see that this is a very small empty space. If you could keep a small sphere, a very small sphere like a bead you take, if you can fit a bead into it, and if you go for a mathematical calculation, you can compare the radius of this sphere and radius of this void. Void is assumed to be spherical here. That means if you keep a sphere, a small sphere fit enough to keep inside, what is the radius ratio? That's very important. Okay, the radius of this void, that is written r void, divided by radius of the particle or radius of the sphere, r by r, that can be easily found to be 0.225. This is very important value. So radius of tetrahedral void is 0.225 times the radius of the sphere, or radius of void by radius of sphere is 0.225. That means roughly this is 0.25 nearly. You can say that the size of this void is roughly 1/4 of the size of the sphere. Okay. Now let us go to the second one, that is octahedral void. So you can see that there are so many such tetrahedral voids all around this lattice. Coming to the octahedral void, the second one, for that you consider another part of this crystal, this arrangement. In the first layer, you consider these particles 1, 2 and 3. Okay, these three spheres of first layer, the blue spheres, I am drawing it here. 1 and here the other 2. Okay, these three spheres, these three spheres. Then touching these three spheres in the second layer, the green spheres, you can see another 3. See, the green spheres 1, 2 and 3, which are touching these three blue spheres. So that comes like this. Actually it comes inverted with respect to the first one. See, in the first layer 2 here and 1 here. In the second layer 2 here and 1 here. It comes like this. Okay, right? These kinds of arrangements are there, so many in this arrangement, in this lattice. Now the empty space at the center here, right? This empty space is called octahedral void. I can show it using the models. See, this one layer, first layer, and this, suppose this is a second layer. There are three spheres coming like this, and one layer, first layer, and this is the second layer, which come inverted like this. Okay, I'm keeping it like this. Okay, so 6 spheres are touching each other. Like in the case of tetrahedral void, if I join the center of all these 6 spheres, see, to understand that, let me hold it a little bit tilted like this, and you look, you can see that 4 spheres make a square, right? And there's one above, this one is above and one is below. If I can show it like this also, doesn't matter, like this also. See, 4 spheres make a square, and one sphere above and one sphere below. So the geometry will come like this. That means in the first layer I take the center of these two, and in the second layer these two center will be of course above. Anyway, let me draw it like this, so you get a square like this. Okay, and then there is one particle here, one above and one below, and that, let me show, shifted like this, and joining from this to all the corners of the square. What you get the geometry as? This is an octahedron. So remember, 6 spheres are touching each other, and there is a vacant space at the center. Of course, this will be much larger than tetrahedral void, because in tetrahedral void the particle is very close, but in octahedral void you can see that these 6 particles, 3 in one layer and 3 in the other layer, they are a little diffused out, a little away from each other, not so close. If you keep it like this, it's very close. If you keep it like this, particles are not that close, not as close as in tetrahedral. So that means the empty space at the center is bigger. That means octahedral void is a little bigger than tetrahedral void. That means you can keep a little bigger bead or spheres inside it. Now this size of the void and the size of sphere can be compared mathematically, and there's a ratio, radius of void divided by radius of sphere, in this case is found to be 0.414, nearly 0.5. That means this void is nearly half the size of the sphere. So if I show this octahedral void, this is the octahedral void, and it will be in this geometry, it will be somewhere here at the center. This is octahedral void. So how you define octahedral void? It is the empty space at the center of 6 touching spheres. So don't get confused when looking at the term octa. Octa means 8. Why? Because this geometry has 8 sides, but the number of spheres included is only 6. Remember that. So vacant space at the center of 6 touching spheres whose centers lie at the corners of a regular octahedron. I repeat, octahedral void is a vacant space at the center of 6 touching spheres whose centers lie at the corners of a regular octahedron, and this is the radius ratio. Okay, so octahedral void is bigger than tetrahedral void. It's an interesting question to ask: how many tetrahedral and octahedral voids are there in the unit cell of a crystal? For example, if you take HCP or if you take CCP, which is most common, you know CCP is same as FCC. How many voids are present? That we can do easily. I will okay, that point we can note it here. The point is that on close examination, it is found that the number of octahedral void is the same as the number of spheres in the crystal, and the number of tetrahedral voids are double the number of spheres. You understand? So based on the number of spheres, effective number of particles, we can calculate. See, for example, in CCP, that is the same as FCC, you know that in a unit cell, effectively there are 4 particles, right? So how many tetrahedral voids are there and how many octahedral voids are there? Number of octahedral void is the same as the number of particles, so there will be 4 octahedral voids. Number of octahedral voids equal 4. Number of tetrahedral voids is equal to double the number of particles, so that will be 8. Okay, so if you take the unit cell of CCP, right, this is CCP or FCC, it's interesting to identify these voids in this close packing or in this crystal. Very interesting. Let us take for example tetrahedral voids. You know, if you calculate the effective number of particles, you know how to get this 4, right? Because there are 8 corners, 1 by 8 into 8, plus at the face centers there are 6 faces, so face center contribution is 1 by 2 into 6, right? That is 1 plus 3 equal 4. So where are these 8 tetrahedral voids? You can see it's very interesting. Look, consider 1, 2, 3 particles in this layer and 1 above it, okay? Or behind this corner particle, okay, this is a corner particle, right? You can see there are 3 particles touching. So what about this void? So there are total 4 particles in touch. So what is this void? This is definitely tetrahedral void, correct? Tetrahedral void. So if you check all around, you can see that behind every corner particle there is a tetrahedral void. That's what? That is the 8 voids, tetrahedral voids in this unit cell. Now coming to octahedral voids, there are 4 octahedral voids. To understand that, see, consider 1, 2, 3, 4. These 4 particles that make a square, right? And 1 above this face center and 1 below this face center. So that means consider the face center particle, that is these 6 particles. How does they look like? They make an octahedron, isn't it? These 4 particles make a square, 1 above, 1 below, so it's an octahedron. So this empty space going inside into the center of this cube, this is an octahedral void, right? So that is 1 octahedral void is there, 1. And what about the remaining 3? Actually, these edge centers, you know this is an edge center, you know there are 12 edges for a cube, right? This is one edge. This edge center, if in close examination, if you extend the unit cell to this side also, you will understand that this is an octahedral void. It's a partial octahedral void, right? If you keep the next particle here and below, above also there is one below, you can see that this is an octahedral void. Like that, all the edge centers are octahedral void. But you know that this edge is shared by how many unit cells? 1 here, 2, above, 2, so it's 4. So what is the contribution from edge center? 1 by 4. So 1 by 4 into how many edges? 12. So what is 1 by 4 into 12? It is 3. So 3 octahedral voids are distributed all over all the edge centers, and there is 1 right in the body center, so total it is 4. So we identified, we located where are the tetrahedral and octahedral voids in the unit cell of FCC or CCP. Okay. Now finally, there is one other type of void which comes seldom, which rarely comes in certain crystals that we may require. What is cubic void? Cubic void is if you have 8 particles. See, if I draw it like this using a cube, it will be more easy. See? Suppose there are particles only at the 8 corners, like this. Particles at the 8 corners you have. Of course, they'll be all in touch. So there are particles at the 8 corners. Let me show with the model. Look at this. This is what? This is a primitive cubic, right? Particles only at the 8 corners. And you can see that there's a very big space inside at the center. This is what is cubic void. Why? Because these 8 particles which are in touch, if you join the center of all these 8 spheres, what do you get? You get a cube. So this void is at the center of this cube. So that's why we call it cubic void. So how you define? Cubic void is the vacant space at the center of 8 touching spheres whose centers lie at the corners of a cube. Okay? If it will be much bigger, of course it is much bigger in size, right? This is much bigger, cubic void. If you take the radius ratio, you can see that radius of void, cubic void by radius of sphere is found to be equal to 0.732, much bigger. Okay, of course it is very clear from the model itself. If you keep particles like this, they are not going into the depressions and all, and there is large, big, very big empty space here. And this kind of void become important in some ionic crystals. We will see that later. So these are various types of voids present in the close packing of crystals. In the next class, we will go to the interesting area of the structure of ionic crystals, where there are different types of particles, there is anion and cation with different size, how we fit them in the lattice. See you in the next class. Thank you.